Hello everyone, in this lecture video I will demonstrate how to start building the dictionary right from the beginning. So the first thing I will do here is to partition the data, and the reason we would like to do that is because we want to independently gauge the performance of our model, which is built upon the training data set, to see that whether it's performing well and whether we can generalize the prediction to the data set that is outside the training data set. So let's go ahead and do that. So I will go to the sample tab here, drag partition node here. I will connect these two and I will make sure that this is highlighted. I will go here. Let's say I want to have 50% of the records in training data set, 50% of the records in validation data set, and I don't want any test data set. So if you run this one here, it's gonna take some time. As you see, it's partitioning the data, that's why it takes some time here. But as soon as you see that green mark here, I guess it is all set. So I will click on results here. So if I go down here, you'll see those statistics here. That is the original data set, and we had a response rate of 0, and we had 4,843 cases and 4,843 cases where we had response rate of 1. So it is 50-50, because initially when we created the model we specified that we want equal response rates, and when you did the partition, so we created two data set, train and validate. In the train data set you have roughly half of this number of rows here for both for the response of yes and no, and here also for the response of 0 and 1 you have more or less equal number of records. The reason you see here 49.98 or here, because you see here we have odd number of cases. So obviously in this one you have one record less, and here you have one record more, because you cannot partition one record into two basically. So with this we are done with the partition data. I will move ahead and start building my decision tree here. So I will drag the decision tree node, go to the model and drag the decision tree node here. Connect these nodes here, and this time I will build the decision tree interactively, which means one step at a time. So you see this interactive here. I will click on these three dots here. It takes a while to open this interactive decision tree window. So here this window is, so if I want to start building my decision tree, I will right click on this one, go to split node here. So this window will show you all the variables and their corresponding log worth values. So basically the higher the log worth, which is this column, the better the split is, which means that this particular variable is the most important variable as of now, because it has the highest log worth compared to all other variables, because it's kind of partitioning the data into two distinct groups, or isolating the data into two distinct groups better than any other variable. So we'll select this one. If you click on edit rule here, it's going to show you how two branches are or will be created. The left branch, which is denoted by this sign, will have all the gift counts which are less than equal to 2 basically, and the right branch will have all the gift count which is greater than equal to 3. So that's why it's 2.5 here. So with this, let's say I want to apply here. So you'll see, I'll say okay here, okay here. So two branches are being created here. So this one has right now, out of 4843 records here or cases, it has 2283 cases, and this node has 2560 cases. So here you see that percentage of responders are very high here, 56%, and percentage of non-responders is very high here, which is almost 57%. So these are two distinct groups. So if you want to, let's say, partition further on this node, right click on it, click on split node. Now you can see the most important variable being the median home value, because it has the highest log worth. So I will select this one, and again, you can apply here. Let me show you something here. Apply here. So okay here. So you see the home value, median home value creates two branches. This is less than $67,350 worth. If the home worth is greater than equal to 67,350, you go right. But one question that might come to your mind is, why 67,350? Why not to just round it up to 70,000? Can do that if you just right click here again, go to split node and select median home value, edit rule here. Let's say I want to create a split at 70,000. So you type it in, add this branch, and then you go ahead and delete this branch here. And if you click on apply, it's gonna create the split at 70,000. So as you see here, decision tree gives you a lot of flexibility to edit the rules if you want. So likewise, you can generate the entire tree, but let's go ahead and create the maximal tree here. So I guess you just right click on the root node and just click on train node. So it will go ahead and create the maximal tree. So obviously you cannot see the maximal tree here. If I right click on it and say view here, fit to the page, you can see almost the entire tree. So such a huge tree is being created. Now let's see the assessment here. So if you go to the view and see sub tree assessment plot here, this assessment plot is showing you the misclassification rate. Now how would you define the misclassification? Misclassification is simply when you predict the response to be 1 but actually it happens to be 0. So that's a misclassification. Likewise, you predict something which is going to be 0 and it turns out to be 1. So that's a misclassification. So basically you want to minimize the misclassification for your decision tree model. And as you see there, as you this x-axis shows you the number of leaves. So initially this is just one, which is the root node, but once you split it into two more nodes, which is 3, you see the misclassification rate is going down. The blue one is for the training data set. We're not going to talk about the red one right now, but as you see that as you keep splitting the tree, this misclassification is going down from 0.5 to almost 0.4 maybe, and looks like it just keep going down for the maximal tree, because your maximal tree has 15 nodes right now. So looks like it's basically telling us that this 15 node tree is what you need because it's giving you the minimum misclassification rate. But you are already getting the glimpse of the performance on the validation data set. This is the validation, red one is the validation data set, and you see that that's not quite true, because in the validation data set looks like it's not going there, it's going up. So we'll come back to this one. We're not going to worry about it right now. but as you see, the blue one is going down and it's suggesting us that this is the best possible tree as of now. So let's go ahead and close this one here. So basically it's closing our interactive decision tree here. It will take a while. So it's done here. What I want to do is we created the maximal tree. Now we want to go ahead and create what we call optimized tree as such. So what we're gonna do here is we're gonna um, um, let me repeat this. We are not creating the optimal tree right now. We are kind of assessing the performance of this maximal tree that we just created on the validation data set, which we kind of already did it, but let's go ahead and formally do that. So I will select this node here. So I will freeze or froze this tree. So use frozen tree. I'm going to say yes here. So doing that, it will not change our maximal tree. Otherwise, it's going to go ahead and start pruning the tree, which we don't want right now. We want to assess the performance of this maximal tree that we just created. So I will right click on it and run this one. Say yes here. Make sure it is set to yes, otherwise you will get different results. So I will click on results here. Now this is our results window. Now it has a lot of plots and statistics. I will explain that later on, but let's go ahead and see how our maximal tree has performed against the validation data set. So we can go here, view model, and let's say subtree assessment plot here. Okay, so I'm gonna maximize this one. So this is average square error, but we are more interested, let's say, in misclassification rate. So I'm going to click on that one, and this shows something which we already have seen. This is a misclassification tree, which means that when you had just one node here, you can bring the cursor here and it's going to show you. So the misclassification was very high, but as you keep adding the number of leaves or keep splitting the tree, you see that it's going down. And for the blue one, which is on the training data set, you can see that it's just going down and down, which is kind of suggesting that the maximal tree is the best tree, because for maximal tree, which is 15 leaves node, the misclassification is lowest. But if you look at the red one, which is which is like applying the maximal tree on the validation data set, it doesn't turn out to be quite so, because you see that after a while this starts going up. Virtually here, after 5 leaf node, you can see that the performance does not improve at all, or it get worse after 11 or 12 nodes. So you can see the difference between the two. So this is definitely a case of what we call model overfitting. It's this blue one is performing extremely well the training data set, but it fails to perform equally well in the validation data set. And that's where this generalization comes into the picture. So how good is our model will be based on the assessment on the validation data set. So optimal tree looks like, should be somewhere around 5 leaves, because after that the performance is not improving. So with this, let's say I want to close this one here, and I want to rename this one. So I'm going to rename this one and call it maximal decision tree. So now let's go ahead and create the optimal tree, which is pruned to the right size. So I will go ahead and drag another decision tree node here, I will connect this one and I will rename this one, let's say, to optimal decision tree. Okay, and then so here what we want to do, we want to develop the optimal tree here. And subtree assessment, this basically tells you how your optimal tree will be selected. So what we are saying here is we're gonna use the assessment algorithm here, and the measure could be decision, average, squared error, or misclassification. So let's say we are going to make a decision, so I'm gonna stick to decision here, and I will right click on this one and run. It's going to run all the nodes again and create our optimal tree here. This time we are not doing it interactively, as you have noticed it. I just dragged the node here, connected it, and everything is default here, and I right click on it and I ran the node. But that was not the case during the maximal tree. Now one question you might ask is, you have to go through the interactive window to create the maximal tree? The answer is no. Virtually you can let me click results here. You can do that. Minimize this one. You can do that maximal tree without going to interactive tree. Here I guess the tree method here, if you select the largest here, it will create the maximal tree for you. But in this case, okay, we already created the tree here, so I will go to the view model subtree assessment plot here. And let's say I'm more interested in misclassification rate. That's a default that will be used for decision making. And as you see that now we see this blue line here, which is telling me that up till this point 5 node tree is the optimal tree, and beyond that your tree performance is not good on the validation data set. So my optimal tree is basically 5 leaf tree, which gives me the same performance as was given by my 15 leaf tree. So I can go ahead and see the results, or let's say I want to see my decision tree here. So I have to close this window here, and this is my results window here, and this is my tree. So if I maximize this one and let's say right click view fit to the page, now this you can see this is my 5 leaf tree. So because it has 1 2 3 4 5 leaves, so this is my optimal 5 leaves tree, which is basically giving me the same performance as was given by my 15 leaf tree. So with this, let me close this one here. Now this one was like, you wanted to make decision whether you want to send the solicitation mail or not. So you will predict whether responders will respond to your mail or not. So based on that we selected the measure here, misclassification rate. But often let's say you want to come up with the probability for each case. So in that case, we might use a different measure to classify. For example, here, what we're gonna select here is in the measure here, we're gonna select the average squared error. Okay, so let's go ahead and do another one here. Let's say I want to create another model here, and I will right click on it, rename it, and say this is probability decision tree. Okay, I'll connect the data partition node to this one, and as discussed, I'm more interested in I'm more interested in developing the tree to assess the probability of the donation, whether particular customer will be a donor, or what is the probability that a particular customer will be a donor. So for that, we generally don't use misclassification rate. We use what we call uh, average squared error. So let's see, where is my, I'm gonna select this one again. Let's say here, splitting rule, subtree assessment. Here I will select average squared error, and I will run this tree here. So let's see the results here. Let me see the subtree assessment here. Now this is the average squared error, and that's what I was interested in looking at. So you see that this is pretty much the same result we got when we used, instead of average squared error, misclassification rate. But although they look very similar, again this is basically telling me that my 5 node tree is the optimal tree, and beyond that, complexity doesn't matter, because even if your 15 lead tree is the most complex tree, it's performing well on the training data set but not so well on the validation data set, which is indicated by red. So my 5 tree is the optimal tree, and we can see this optimal tree, although this looks very similar to what we did last time with our optimal tree, but we use a different measure, misclassification rate. But in this case we are using average squared error. But although the number of leaves are same, the tree is not. And we can go here and check it out. See, this tree is different. So depending on what is the assessment measure you are using, your tree will be constructed accordingly. So this is different than the assessment measure that you used earlier, um, which was misclassification rate, and here it is average square error. So that is something you have to keep in mind. So when the objective is to make decisions, whether somebody will be a donor or non-donor, you use misclassification rate. When you want to come up with a detailed probabilities for each case or each customer, like what is the probability that particular customer will donate the money. So in that case, you want to use something called average squared error as the model assessment measure, because that will create unbiased model as such. So with this, let me close this one here. Next, we will explore the results window, which I haven't explained it so far, but let's go ahead and see those results. So this was the results window we got, and we never explained this thing. So let me go ahead and start explaining each window in a nutshell, so that you understand what exactly is going on in this window. So let's do. Before I explain all these plots, I want to explain something here. I will go ahead and show you this maximal tree here again. Now, one thing that might come to your mind is the color. So what does this white color, blue color, dark blue, light blue color indicates? Now, the lighter the color, that means it has more cases with the more response rate. So for example, if you compare this to one, this one has a higher response rate, 46.7%, compared to this one, which has only 36.1. We will, when it comes to the color, we always focus on training data set, not the validation. So likewise, if something is white, that has the highest response rate. So if you go here, this one has the most number of cases, if I'm saying that right. So comparatively, other things. So I guess intensity The color intensity also shows the number of cases that you have, and the response rate within. uh, don't be confused by this percentage. When I say light color means the total number of cases that you have with the response rate of 1. If those cases are higher, the node will be lighter in color. For example, this one is white in color, which means that almost 50% of these records are the responders. So here, if you take 64% of 657, that's going to be way less, maybe around 400 records, which is much lesser than 2400 something here. And likewise here, 48% of 1011 is almost 500 records. That's way more than here. So it's a total number of cases with the response rate in a particular node that decides the color of that node. Now let's go ahead and now let's explore the tree map here. Tree map is basically shows you your entire decision tree. So this is the root node, which being split into two nodes, and if you take the left node, that's being split into two more nodes. Right node is being split into two more nodes, and then you take this node, it's been split into two more nodes. So that's your 5-leaf decision tree: 1 leaf, 2 leaf, 3 leaf, 4 leaf. So you have to count the eight nodes to count the number of leaves. Now the size of this box determine the cases that you have in those nodes. For example, if you hover on this one, it says that you have 657 cases compared to this one. This is bigger rectangle, which means that it has more number of cases. So size of the rectangle denotes the the size of the data set in that particular node. The and again, when you're saying the data set, you're talking about the training data set, not the validation data set. So that's a tree map. That's how you interpret the tree map here. Let's do the leaf statistics here. This basically shows you the one that you predicted and the one that actually turns out to be. So the one you predicted was in the blue one, and the one actually turns out to be in the validation data set is indicated by the red one. So basically it tells you that if bigger the difference between two bars, indicates the model is not doing as well. You want this both bar to be of equal size if possible. Now, as you see, this was your leaf number 1, 2, 3, 4, 5 leaf. Now, the length of this leaf is more than the leaf number 2, which simply means that this has more number of cases compared to second leaf. This one has more number of cases compared to this one. This one has more number of cases compared to this leaf here. And this leaf has the lowest number of cases as such. So this is how you interpret the leaf statistics here. So let me do this one. So let's do the cumulative lift here. Now this chart is the most difficult chart to interpret and make sense out of it. Now basically what it does is it takes all the cases in the training and the validation data set, although you are more interested in looking at the validation data set as such. So it takes all the cases and you have estimated the probabilities for each case. And what it does, it takes all those probabilities and sort them in the descending order, so that you get the cases at the top which has the most probability that the customer will respond. So those are indicated by this 20% here, which means that top 20% of the cases, then next 20%, then next 20%, and henceforth. So this top 20% of the cases basically are saying that these are the customer where the probability of response is highest. So basically this is more interested in case of marketing scenario where you have limited budget and you only want to send out the solicitation to those customer where the probability of response is higher. So you can use this lift chart and find the cutoff time I mean the cutoff window that will show you, like, how many mails you can send out to the customers will uh, who will tend to respond better compared to the other data set. So this is how I would interpret the lift chart. Basically, lift is the ratio of the top cases versus the overall cases, which means that if you take top 20% of the cases, let's say you have 100 customers, and you find out the probabilities of response for each customer, and then you sort it in the descending order. You take 20 cases with the highest probability and divide it by, if you choose randomly 20 customers, and and whatever you get the probability for those. So if you divide these two things, you get the cumulative lift as such. So this is how I would interpret the cumulative lift here. Let's go ahead and do the next one here. Fit statistics is by far the most important statistics, I would say. You want to focus here on the misclassification rate and the average squared error. So you want them to be as low as possible, and at the same time, you want to make sure that the misclassification rate or the average square rate should be virtually same for the validation and the training data set. If there is a huge difference between these two values, then that means there is something not correct with the model, and you would like to go back and adjust the properties. So you see here, these two values are similar up to, I guess, 3 decimal places, and these values are similar to almost, 3, or if not 2 accurate, and then the third decimal place it starts differing, but overall you want them to be as close as possible. And also, the lower the better. So if you are targeting average square error, which is the case in this case, I want this errors to be as small as possible. So this is how you would interpret this fit statistics here. Now let's see another important thing, variable importance. So you go to the view model and choose variable importance. This will show you all the variables in the order of their importance level. For example, you see that the most important label was the gift count 36 with the importance of 1, and then the next one is gift average last, right? And then median home value, and henceforth. So these are the top 4 most important variable in the model. This importance statistics basically tells you that the amount of variability in the target that is being explained by the corresponding input variable. So this means that this variable explains 52% of the variability in my target values. This one 50%, this one is 48%. But overall, this tells you, the number of variables, input variables, which are very important in this model. So this is another thing that you would like to keep in mind here. Next one is the output window. If you maximize this one here, you can see a lot of details here. For example, this shows you the number of variables that's being used. We have 2 binary variables, we have 20 interval variables, 3 nominal input variables. These are all input variables, and we have 1 binary target variable. So it shows you the event of interest is 1, which means that 1 is the response rate, and you have to pay attention here because it's not saying 0 here, it's saying 1, which means that 1 is what indicates that the donor will donate money. If in case you in your data set you have 0, that indicates whether the donor is going to donate the money or not. So if 0 indicates the response rate, then you have to make sure that the event of interest is 0, not 1. Again, here 1 indicates that particular customer will donate the money or he will respond. So that's event of interest is 1 here, and we have a number of labels as 2 because it's binary. And here you can see the variable importance again. These are the 4 variables of high importance that we saw in the variable importance output there. Same thing here. This is the tree leaf report. These are your 5 leaf, the best leaf, the optimal tree in the optimal tree. It shows you the training observations and the validation observation in terms of percentage as well. So you can see those things there. And this is the fit statistics that we have already seen there, right? So this one is sum of squared errors. This one is misclassification rate that we have already seen, right, in the previous charts. So likewise, you can go through all of them. These are basically summarizing whatever you have done so far in the chart. So this is how you would develop the tree and interpret these different charts. And with this, I would stop my training lecture video here. Thank you very much for listening.